Hey, so this video is meant to help you get started in doing the project for linear algebra. So I will have posted, by the time you're watching this video, a zip file on Canvas for the project that you can download. So I've downloaded that to my desktop here, linearalgebraproject.zip. So maybe I should mention here, I use Linux as my operating system, so things look a little bit different here, but like all of the same stuff will work for you as well. But this is a zip file, so you need to extract it. I can extract it like this, which goes to the other monitor, of course, to make the actual folder, right? So however you extract zip files in your operating system. And then so if you look into this, you'll see that we've got a folder, Project 2020, and then you have course, Project Linear Algebra this, and then you have a picture of Gilbert's strang, right? So this is going to be used inside this project. And this file here is a Jupyter notebook, which we'll see more about in a second, but it enables us to have writing and programming in the same document. All right, so I'm just leaving this on my desktop. But you know, wherever you need it, we're about to load it into CoCalc, which is what we're going to use to actually run it. Okay, so you've downloaded that, you've extracted it, you know where it's stored. I'm going to pull up Google and go to CoCalc. Oops. CoCalc. Okay, so it automatically logs me in. If you don't have an account yet, then you can create one for free. You should not have to pay any money whatsoever for doing this project. So take the free option for the account, and then you can bring up your projects, and you want to bring up the project screen, and then just go to create a new project, and we'll call this linear algebra demo, whatever you want to call it, right? You probably only have one. So I'm going to create this, and this should give me a directory. So it's just basically a folder here. All right, and so as soon as you can, I'm going to upload those two files that were inside, right? So these are the course project there. So you can see, okay, great. And then you also want to upload the picture of Gilbert's strang, because that's actually going to be used in doing your project. Okay, so then, all right, we've got those. I'm going to go ahead and open the course project linear algebra. So this is simultaneously the directions and also for you to fill it in. So you'll see something like this. This is just a mismatch in the Julia versions. So you can click, everything will work out fine using Julia 1.41 instead of 1.4. Okay, so this is what's called a Jupyter notebook, and it's just, you can see that it's organized into things called cells, right? So it's kind of like Excel or something. So each one of these is like a block here that I'm clicking on, and they can either be code or markdown. Those are the only two that I ever use. Markdown is for writing stuff, so like I put in a title here, course project for linear algebra, blah blah blah, notes and tutorials, and then some writing, right? So this is also a markdown box. The code ones, which is specified here as code, allow you to actually program in Julia and stuff. And if you're scared by the term programming, don't be, because you're not really going to do much programming. It's programming in the sense that you've been doing with MATLAB or Octave or anything else, right? So we're going to use Julia as a very fancy calculator. But we need to tell it that Julia can be used for many things, so we need to tell it that we're going to use it for math stuff and a little bit of image processing. That's where Gilbert's strang is going to come in. So this box here, which I give to you, is importing the libraries that we need for this. And the really important thing here is, so if you're falling asleep already, then wake up, is Every time you reopen this document, you need to run the code. Just because it's there doesn't mean that it's run through and it's been loaded into memory. So I'm going to do Shift Enter here. You could also click Run up here with that highlighted. But with the cursor in that block, if you do Shift Enter, and you can see this box over here turns green to let me know that that code is running. And this first one may take a couple of minutes to actually run, and that just has to do with the way that Julia is designed, and also because we're using the free version of the CodeCalc here. Okay, so as you go through, right? So once this finishes, then I'm going to do Shift Enter. You can have more than one queued up, right? So this one's waiting to run until that is done. But you'll need to go through and run these. So if you get some errors or something, then make sure that you've progressed through this. You can certainly save your progress and things and come back, but every time you do, you're going to need to run the cells in the notebook. I think there may even be a button here that says, see if I can figure this out live. Don't need that. You'd think that there was a button that would allow you to, oh yeah, run all. So you could just hit this when you first log in, and that will run every cell in the notebook. And that way you'll have all of the stuff loaded in, you'll have things defined. So I'm going to let you obviously read through this. I've tried to make it as plain as absolutely possible here. We're basically just learning how to do some linear algebra, and then there'll be a few applications of it as you move through. But this first cell here, this is how do you put in a matrix into Julia? So you just do spaces for between rows. So this is this matrix in Julia. So 1, 2, 4 with spaces, colon lets it know we're done with the first row, 4, 6, 7, blah, blah, blah. So a row vector would then be 1, 1, 1, a column, B column would be 1, semicolon, 1, etc., right? So now I need to run that, so Shift Enter, or like I said here, you could go here and then click that. And then, oh yeah, so these cells you can also run. But you shouldn't really need to edit those. The markdown cells are just me giving you guys some guidance or explaining what the hell I'm doing. And then of course, so we can do A times B column. So that would be a matrix applied to the vector, right? So we just did a matrix multiplication of this matrix times this column vector. I could also do the row on the left-hand side. That actually makes sense, and I'll get out a row vector, which you can see it shows me a row vector. Matrix times matrix is very easy as well, right? So if I do the multiplication sign and both of them are matrices, then I get a matrix out, right? So that would be the matrix A squared, or A composed with A. And then if you see something like this, just worth pointing out, so this is an illegal multiplication, right? Like A times that row vector does not make sense, right? They don't match up. So this is what Julia is telling us here, that like the math does not make sense. A times that row vector, that's a 3 by 3 times a 1 by 3, right? So the inner dimensions don't match. All right, so some other stuff. If you want to take the transpose of a matrix, you just do the little dash, or the single quote right next to your shift key on the right hand side there. And I think that's the same as the term in MATLAB. And then just to show you here, right, so here's a matrix identity that we know, A, X, quantity transpose, so you reverse the order and multiply. So we could do A times B column transpose, and we want to know, so the equal is does this equal? It's a logical equal, it'll return either true or false. And so this says, yep, that's true, at least for this one case. And just one more that you might be interested in knowing is how to find the rank of a matrix. Rank of A gives you the rank of our matrix. So our 3 by 3 matrix has rank 3. All right, so here we've arrived at our first question for your project, right? At this point, you've just been sort of going through and learning how to use it. And so you can see that I've tried to label these pretty obviously. Question, this, and then there's a box here that's code for you to put in your answer to the first question. Right? So it just says create a matrix B, this, and then find this product of the A times B, B, A, right? So you're going to just say something like B equals 1, 0, 1, semicolon, for the first row, 1, 1, 0, 0, 1, 3, and then A times B times B times A. Boom. So there you go, right? If you're still watching, then that's the solution to the first question. It's not a terribly difficult one. But just to get you warmed up in how to use Julia to facilitate our computations. All right, so then the next thing that we'd show you how to do is to do the solve, right? Which this is the same syntax that you had in MATLAB. So if I want to solve the AX equals B, I do A backslash B, right? And then I can save that solution as solution. So once again, even though I can see this output, it hasn't been run yet since I've reloaded this notebook. So I need to run each one of these if I want to use any of these components. Okay, so then question 2, that solve the system A times BX equals B. All right, so I'm going to let you do that one, but here's where your solution would go, right? And then you should be able to run it and show me that you've solved the solution. All right, so then that kind of wraps up the mechanics. We get most of the basics that you need for solving linear systems and commands. The rest of them we'll do sort of on the fly. This brings us to our first application, least square solutions. And so the idea here that I'm setting up is that these dots are data that we've recorded for some projectile motion. And the blue line, we don't actually know that, but like that's what it truly was if we had perfect measurements, right? If our physics lab skills were of infinite precision. All right, and then, so I kind of go through what does it mean to set up a least squares for a polynomial like this. So this is a quadratic polynomial that we're fitting. So we want the initial height, the initial velocity, and then g. So it's much like linear least squares, where we have 1 and then the this should be t1 squared. Try to fix that before I upload it. Equals, and then our data, right? So this creates that matrix M for you. And then we're going to walk through how to solve this. All right, so that is a fully solved out solution, which leads us to, I want you to go ahead and program in, using the same math here, the least square solution to just a linear problem, right? So here's my overdetermined system. So you're going to need to put this in, right? So you're going to start here and say, I don't know, L for my least squares matrix, 1, 1, 1, 2, dot, 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 right, for that matrix, and then my B least squares, so that's my right-hand side, is 1, oops, first row is 1, second is 2.1, 3.9, etc., right? So you can fill those in, and then remember how you do a least squares, right? So I review that up here, but it's going to be L transpose times L backslash L transpose BLS. Why? I'm going to let you figure that. I'm going to let you do that part. Okay, so then we could also use Julia to find the eigenvalues and eigenvectors, which is the last topic that we covered in class. And this is where numerical linear algebra becomes very useful, because eigenvalues and eigenvectors are a big pain in the butt to find by hand. So just for a 2x2 matrix, we can find the eigenvalues and eigenvectors. You get 2 eigenvalues and two vectors of length 2 for the eigenvectors. And so here I just want you to practice putting this in, right? So define a 3 by 3 matrix and find the eigenvalues of it. Okay, so then you're going to do the Leslie matrix version of this. All right, so this is a whole application, but basically we're just going to define this matrix, which this code here does for you. All right, so this just sets up so you don't have to type this in. And we can use this to forecast populations, right? So I kind of ask you to work through that a little bit. So I want you to, here I just want you to define a new starting population. So you're just going to copy and paste this down here. Oops. I don't know why that didn't copy and paste, but copy this down there and then change your initial, your x0 to something else. All right, and then I go through a whole explanation here about how we can use eigenvalues and eigenvectors to find out what the long-term dynamics of our population will be. So that it turns out that if all the eigenvalues are inside the unit circle, then it means that population is going to go extinct. And we can tell that without having to run a bunch of simulations and start it from many different initial conditions. And then we implement a conservation program, and I want you to use what I've shown you up here, so you're going to copy and paste again a lot of it. So we just redefine our matrix, start from the same initial population, and we're going to see if we can save the bird species. Because if the eigenvalues live outside if there's at least one that lives outside the unit circle, then that means the population will grow over time. Okay, and then this brings us to the very last problem, I think, which is going to be the image processing, and this is where we needed to upload the Gilbert-Strang picture, because we're going to do something with a picture of Gilbert-Strang. Okay, and so we actually talked about this a long time ago in class, but the idea here is we're going to compress images using linear algebra. So you can load in a grayscaled image of Gilbert-Strang in Julia. So this kind of loads it in as an image, but an image we can view, especially a grayscale image, we can view as a matrix, right? So this just shows me the matrix that corresponds to this picture of Gilbert-Strang, where the entries in the matrix, so it's the pixels by pixels, and then these entries tell me like how dark or light it is, right? So I think they go between 0 and 1, and 0 being like, I don't know, white, and black being 1. And so that can then be translated back into an image. And so if you want to see the image version of a matrix that's scaled this way, then you just do gray dot image map, right? So the idea of, and what's gone over in the notes up there, is that we want to do these rank approximations, which means we're going to drop off some of the components of the image. And that allows us to save a lot on storage. And this, so you're just going to use this function that I've written here to do it for you. So this, right now, it saves the first 120 components. Out of 193 total. 193 would be, we don't drop anything. So that's pretty much identical to the full image that we saw above. Let's do it for just 20. A little blurry, right? But it's kind of surprising. So that's 20 out of 193. It's a pretty small amount, roughly 10% of the storage is going to be needed here. And we get pretty close, right? I mean, like sort of surprisingly close. And so what I want you to do is to sort of explore what it means to compress. So here, keep just one component. So that means, see if I can get the copy and paste to work. So what does this look like for 1? That really doesn't look like Gilbert-Strang, although you can kind of see. So you're going to slowly reveal here, and then I ask you to sort of figure out, well, how many do you think there are needed, right? And there's not an exact, I'm not looking for 51.6 or something. Obviously joking because it has to be an integer, but like, I just want you to sort of show me that you've tried to tune it in there, right? And that there is a bit of a balance as far as how many components are actually going to be needed. And the last bit here, there's not a question associated with it, but I just wanted to show you a plot of the singular values, which are what we're using to filter here. And you can see most images turn out like this, where they'd say that most of the power in it is in the first few values, which is why we can get pretty close by keeping 20 of these, right? So that's saying we're going to cut this off at 20, and so we're losing mostly noise there, or mostly things that aren't perceptible to the human eye. Okay, so hopefully this has been helpful. Loading everything in and going through it, I've tried to make it as self-explanatory as possible, but let me know if you have problems.